Welcome. Thanks everybody for coming. I want to just sort of start off by inviting questions as we go. I think we'll also have time for questions at the end. So if it's sort of like not on topic, maybe save it for the end. But yeah, if things are feeling like they could use a little bit of extra clarity as we go, do feel free to interrupt. I can't see the chat while I'm presenting. So if there's questions in the chat, if somebody could surface those, just by speaking. I'll hear the hand raise signal, but do feel free just to like jump in and interrupt me. So we did a little poll before I started working on the slides, just to get a sense of what people were most interested in hearing about. There's sort of a lot of things that we could do with an hour. And the results are relatively across the board. And so we're going to do a kind of survey of, like I said a second ago, what we've done so far, what we're doing right now, what we're going to be doing in the future. And as we go, there's going to be a whole pile of links so that you can dive into these things in more detail. So guiding questions, what have we built so far? What can you do with RISC Zero? And what are we working on now? So a little bit of a sort of preview of what we're going to get into. RISC Zero has built this RISC Zero ZKVM, which is intended as a really user-friendly method of proving arbitrary Rust code. In theory, the ZKVM can support any language that compiles to RISC-V, which includes a lot more than just Rust. But in practice, we're sort of operating in a Rust-first framework. So at the moment, proving arbitrary Rust code is what we're doing. So what can you do with RISC Zero? You can start building zero-knowledge applications without having to think about these really hard questions of cryptography, circuit design, learning custom languages. The intent is to make it as easy as possible for non-cryptographers to get started building ZK applications. And what we're working on right now is making it so that those applications can also integrate easily with on-chain applications. So we're working on this product called Bonsai, which is a ZK proving service where you can write ZK applications that will interact with, first will be things on Ethereum, and we'll see what other chains we end up supporting. So any high-level questions before we'll go into these in like a substantial amount of more detail, but if anything's unclear at this point, feel free to ask.
One quick reminder or update, the Telegram poll is even more accurate, like same weight for all 4 questions.
Oh, really?
Yeah, it's almost even now.
Okay, yeah, I took that a little bit out of date. Thanks for the update. Okay, so a little outline of the talk. We're going to start with a kind of intro to the ZKVM. And then we're going to dive into what is happening like right now. I think maybe last night, maybe this morning, maybe later today, certainly like in the very near moment, we're releasing our 0.15 release, which includes this feature called continuations, which is really exciting. And we'll talk a little bit about the other features. And then we'll dive into Bonsai. So in the intro, we're going to look at a few specific examples. We're going to look at a proof of checkmate and a proof of like entry in a JSON file. We're going to talk a little bit about what Rust crates work and don't work. We're going to talk about performance of the ZKVM, and we'll touch on the proof system. Like diving into the proof system could easily be a whole hour in and of itself. So this will really be a survey of the proof system rather than a kind of deep dive. Continuations is really exciting. It unlocks a lot of new possibilities. In particular, we have a working example of fully homomorphic encryption inside the ZKVM right now. We have a working example of the EVM running inside the ZKVM, and we have a working example of WASM running inside the ZKVM right now. So these are in the slides that are in the Telegram channel. These are clickable links, and you can see more of those. In the upcoming features department, we just added a big arithmetic circuit, which means that we'll soon be able to do elliptic curve operations inside the ZKVM. Well, I guess technically technically, we actually can already do elliptic curve operations using continuations, but we'll save the details there for a little later. And we are working on a domain-specific language for custom circuits, for both for us internally to write new versions of this circuit and also for external people to be able to add accelerator circuits for custom hash functions and things like that. So that's the preview, and now the rest of the talk we're just going to sort of dive into those things in a bit more detail. So I think this part is going to be a little bit. Oh yeah, Orest, your hand's up. What's up?
Why build another DSL? How would it be different from the ones around?
From the one we have right now? Or what do you mean by the ones around?
Things like and stuff like that.
So the DSL is it's for building circuits. It is like, it handles the types around columns and how those columns interact within. Does that answer your question?
Okay, so a lower level of abstraction.
Yeah, this is primarily like users are going to be writing still in Rust, but if you want to add support for a hash function that isn't in our circuit, and you want to somehow make the circuit, in order to enable the circuit to be more modular, we're building a DSL to allow some more customization there.
Makes sense, thanks.
Mm-hmm. So this is probably more elementary than is appropriate for this group, but I just want to sort of briefly give a high-level motivation for why ZKVMs and what we're doing here. Ultimately, like, I think the whole industry is working to unlock verifiable computation. So if you want to delegate some computation, you have for some reason, you don't want to run a computation on your own machine, you want someone else to run it. Typically, you're going to send it to Amazon, and they're going to send you back the result. But they might lie about the result, and they might steal your secrets. So if you have some private data, you might not want to delegate that computation to Amazon. A sort of flip side of the same script, if someone else runs a computation and sends you the result, why should you trust the result? The status quo is you just sort of have to trust that they're doing what they said they did. Or you could rerun the computation yourself, which is what happens in, I guess, blockchain applications typically. And the future that we're moving towards is that instead of having to rely on trust and instead of having to rely on rerunning the computation, you can just very quickly check a receipt. So questions about this sort of basic introduction to verifiable computation? So a little more visual frame for how this sort of operates. In the top part of this image, I'm going to be showing like what this looks like in the status quo. And in the bottom half is what this looks like with RISC Zero or with another ZKVM. Typically, we have some code, we send it to Amazon, Amazon sends us the results, and then we would send that result to a third party. The third party might be skeptical about whether that result is trustworthy. With RISC Zero, instead of sending the result to Amazon, you send the code, or instead of sending your code to Amazon, you feed your code into the ZKVM, and the ZKVM produces both the result and a proof of that result. And instead of just sending the result to a third party, we send the whole receipt to a third party. And the third party is then able to check the validity of this receipt. So this computation may have secret data. In the first scenario here, we would send it to Amazon. In the second scenario here, we just need to feed it into the ZKVM. And I'll emphasize that this whole part in yellow here can be run entirely locally, which means that the secret data doesn't have to ever actually leave your machine in the context of running a ZKVM locally. So being able to run the ZKVM locally provides privacy, and being able to check the receipt provides scalability, is the sort of high-level view of what ZKPs and ZKVMs are bringing to the blockchain world. So I want to emphasize here the ZKVM part here, because there are a few different ways that we could approach verifiable computation. And ZKVM is a sort of, I mean, I'm talking to Scroll, I guess, so you're familiar with ZKVMs as a model, but I just sort of want to like motivate this because I think for a lot of people who are coming across ZKVMs and ZKEVMs, it's a little bit unfamiliar, the difference between the, I guess, the older techniques or for developing ZKPs versus this ZKVM approach. And the thing I want to emphasize here, I guess, is that the user in this approach doesn't need to touch circuits. There's just the one circuit here, and that's the one that is the ZKVM. And the app developer doesn't need to write their own circuit. They're just feeding code into that circuit. So the basic way, I guess, to create a ZKP is to write an arithmetic circuit directly. That method is hard because writing arithmetic circuits is hard. A second approach is to write in a custom language that compiles to an arithmetic circuit. And a third approach is to use a ZKVM, in which case you just are writing guessed code. So I just wanted to sort of highlight the point that app developers don't need to be thinking about circuit design. Questions about that? Okay. So let's get into RISC Zero a little bit more specifically. RISC Zero is a general purpose ZKVM, and our kind of emphasis is making things as easy as possible for developers to start building. So RISC Zero, by taking advantage of RISC-V and taking advantage of Rust, we're able to offer quite easy onboarding and quite a mature software ecosystem. So in contrast, if you're deciding to build with Starkware, you're going to be writing in Cairo. If you're deciding to build with Alio, you're going to be writing in Leo. If you're deciding to build with Polygon Maiden, you're going to be writing in Maiden assembly language. These require you to learn a new language, and they don't have the like existing package ecosystem that exists in Rust. So by choosing to build on RISC Zero, you're able to build in Rust, which means that you can use familiar syntax, and you can critically import packages. And this ability to import packages is like incredibly powerful in leveraging software. Like the idea that you don't have to build everything from scratch and we can import packages is huge. So we'll see that a little bit more as we move forward. Questions here?
Does that mean that you can support any Rust code, or is there any limitation on the Rust itself?
Yeah, that's a great question. And I think it's not quite the next slide, but I'm going to talk a little bit more about what Rust code will and won't work. So we have this examples repo, and we're going to sort of take a quick look at a few of the examples in this repo, and I'll touch on that question about what Rust code will and won't work. So let's take a look at a specific example here. This is a proof of checkmate. So you start with a chess position and a mate in one that the person generating the proof knows. And the prover here is going to be able to generate a proof that there is a mate in one on the board without revealing the mate in one. And you're looking at, like, from lines 23 to 35 here that's the code for the ZKVM. That's the code for for actually generating the proof. And what's going on here is we import a couple of Rust crates, and then we use this env read command in order to send data into the ZKVM. So this is sending data from the host to the guest. And then we do some computation inside the guest. And then we commit to an initial state, meaning we like put this in the output of our proof. In the journal is where this ends up. And there's this assert statement at the end. And if there's actually a checkmate, this code will manage to complete and will get a proof that includes a commitment to the chessboard in question. And if that assert statement fails, then this won't fail to complete and we won't be able to generate a proof. So here's our proof of checkmate. And I've highlighted, I guess, the importing Rust crates and the how to get information into the ZKVM and how to kind of get information into the public outputs of your proof. So this is our first example of a ZKVM program. Questions? So the next example that I have here is a JSON example. Here we prove some entry of some JSON value matches some critical data. And again, we import a crate, we import another crate. We use this env read command in order to get information from the host to the guest. We use this env commit command in order to get information from the guest into the proof. So the last couple examples that we showed import Rust crates. You may find if you start building on your own that not all Rust crates work. We have been working on this. Each night we test compatibility of the top 1,000 Rust crates. And right now, 71.4% of those are working. So there are some that are not. Usually these are relatively like, we just kind of need to manually do some patching. They might not recognize RISC-V as a target output, or there might be some 64 versus 32-bit situation that like, so there are frequently we'll run into a situation where we try to import a crate, run into some obstacle, and then have to take some time to figure out how to fix that. But the like, aside from this like crate functionality, I'm not aware of any other like feature of Rust code that doesn't work. So does that answer your question about what Rust code you can use? Feel free to tag on with more if there's specifics.
Yeah, that's very helpful. I'm particularly interested in, say, the arithmetic libraries such as Hello Tools and the elliptic curves, etc. I guess you mentioned earlier that some of the ECs are not there yet.
Yeah, so the elliptic curve stuff, historically, the elliptic curve operations took too many. We have this limitation that I'll talk about in a minute, or we had this limitation that I'll talk about in a minute of we could only support proofs for executions that were under, I think the cap was something like 4 million instruction cycles. And the elliptic curve stuff ran over that limit. At this point, you can run elliptic curve stuff because we have removed that limitation, but we'll be able to get a lot better performance once we add support for big integer arithmetic. That's so.
Cool, thanks.
Yeah.
So is the reason why some crates fail that they don't target RISC-V correctly? Is that the only reason?
I'm not going to say that that's the only reason. That is a reason that has come up. I don't know that I'm like most equipped to be able to answer that question of why some crates work and some crates don't. To be real, my like background is more mathematics than software, so a lot of the like heavy software questions are a little outside my realm.
I can jump in there for a second if you don't mind,
Sure.
Paul.
Yeah.
So one of the major things there is just system calls. So we only support a subset of all potential system calls. You can imagine things like atomics or file system calls that we don't currently support. And if a particular crate leans on that to do something, then it's not going to work.
Gotcha. Thanks.
And also another question, if comparing with, the yield curve library versus specifically optimized yield curve library or specific circuit, what's the efficiency comparison, running directly the RISC code, RISC algorithm for yield curve versus a specific circuit for yield curve operation? Do you have any numbers in mind? How is that 100 times more terrible or 10 times or yeah?
Yeah, I think our big int arithmetic, so we're still we've written the big int arithmetic accelerator circuit and are now working on translating that to the elliptic curve setting. So I don't know that we're quite in a position to be able to make that apples to apples comparison. Yeah, I think we'll have to report on that when we have more data.
Okay.
So I do want to comment a bit on the performance of the ZKVM. These numbers are a little bit out of date. In particular, they're from before continuations, but they're only a month or so out of date. So we ran benchmarks on a number of different machines. I've just grabbed the benchmark from running Metal, so with GPU acceleration on an M2 MacBook. If you click the link here, this datasheet link has CPU and GPU performance numbers on a number of different machines. But just in order to sort of be able to orient you to what you're looking at here, I just wanted to focus on one. The far left column here, cycles, refers to the length of execution of the program. So we could either have the length of executions here are ranging from 32,000 cycles to 2 million cycles. And the proof time for those is ranging from about a second to about 20 seconds. You can see the RAM numbers here. The memory requirements get quite large for large programs. This I'm just highlighting now. This is pre-continuations. In our updated world, these memory numbers we'll talk about a little bit more, but they won't be blowing up. Proof size is between 200 and 300 kilobytes right now. We're working on a snark wrapper for our Stark proofs to be able to bring that proof size down to a more practical number for on-chain purposes. And we're just about at 100 kilohertz. That's I haven't yet seen a printout that exceeds 100 kilohertz for the speed of our machine. But I imagine that we might be there now with the most recent updates. So a little orientation to okay, what's a program of 32,000 cycles versus 2 million cycles? Can we orient that in terms of some use cases? So this table at the bottom left here makes some attempt to kind of contextualize those cycle counts with some use cases. So the chess example that we looked at before takes 256,000 cycles, which means the proof will take about 3 seconds. The JSON example that we saw before, it takes 64,000 cycles, so the proof would take about 1.5 seconds.
And what does EVM mean? Is that specific transaction type or?
Yeah, we have there is an example in our examples repo that's called EVM. And it's, I think, running I think that example is one running a single example or a single transaction. I'm not sure what that EVM example is actually. That tag to me is referencing that's the example in our, but I'm not sure. Andrew, do you know what the EVM example is actually doing?
Yeah, it does a single ERC20 transfer using REVM, which is the core of REF.
Cool.
And another quick question is that is there any particular reason why the speed becomes like faster and faster as you grow? Like the speed, the frequency seems like increasing.
Probably
Yeah.
an overhead.
Oh, yeah, it seems like the poor time grow like in accordance with the cycles, like it's double cycle, double poor time. But I don't know what do you mean by speed? Like there, it seems like the frequency differs a lot.
The speed numbers are like, these numbers look quite different across the GPU versus CPU and across different machines. So I don't know that I can give a simple answer to that question. I think it is a little messier than, or it's either messier or I don't quite understand the simplicity yet. So
The prover time is sublinear as well in the cycles, right?
yeah. The prover time is, yeah, it's n log n, which is more than linear. It
And it
does.
goes slower than the cycles.
Yeah, when cycles is doubling, prover time is less than doubling. I feel like I have to think about that offline to be able to conceptualize that right now. I'm feeling a little, yeah, I don't feel like I have immediate access to insight on that.
Cool.
So let's push forward. We have a decent amount of stuff to cover. I don't want to get too lost in the proof system. We have a Stark-based system. When you run the ZKVM, you get a receipt that consists of a journal and a seal. The journal is the like public outputs of the program, and the seal is the Stark itself. So at a real bird's eye view, what do we do to generate the seal? We execute a binary file in the ZKVM, and we get an execution trace from that. We take the columns of that execution trace, and we do this Reed-Solomon encoding, aka low degree extension. Then we do some Stark math. I'm not going to get into the details of what happens inside Starks in this context. And then we use the Fry protocol to convince the verifier that the result is a valid Reed-Solomon code word. So at a slightly more succinct level, we generate a trace, we turn the trace columns into trace blocks, and then we put those blocks into Merkle trees. We do some quotients, and then we use the Fry protocol. So these are clickable links to reference pages and study club videos. We have a lot of content at this point explaining our proof system. We have sequence diagram. We have this Stark by hand explainer. If you do want to dive deeper into the like internals of Starks, I do recommend this Stark by hand explainer. It's like a spreadsheet version of a Stark. You can walk through the like constraints. You can click behind the formulas and see. And we also have this study club series, which includes an introduction to finite fields, an introduction to Reed-Solomon codes, an introduction to number theoretic transforms, a couple videos about the Fry protocol. So I want to, I guess, like just point you to these resources rather than diving too deep into the weeds of this during this talk. But if there are any like particular curiosities about our proof system that I can shed light on, I'm happy to. No proof system questions? Okay. So let's dive into continuations a little bit. This is a feature that we're really quite excited about. It's been something we've been working on for a while, and it is now working and pretty powerful. So let's talk about what they are and why you should care. Continuations are a mechanism for taking a really long program and splitting it into chunks, which we call segments, and then proving those segments independently. So what you get out of this is you can parallelize the proving of those chunks. You can run as complicated logic as you want inside the ZKVM. We used to have this limit of you can only run programs that are so big, but now if it's too big, we can just split it up. It enables this really interesting option of pausing and resuming the ZKVM. So this, I think, unlocks quite a wide collection of use cases. It'll be interesting to see how this unfolds in as people start playing with it. But the idea that you can sort of set it sort of functions as Docker for a ZKVM program. You can run it and pause, and you can prove this chunk of the execution, and then later maybe a different person can continue interacting with it. It sort of opens up quite a lot in terms of changing the model from we can just make a proof of one giant thing to we can flexibly chunk how we want to be thinking about these proofs. And lastly, and quite importantly, it limits the memory requirements to a fixed amount. So it used to be the case that some of our examples wouldn't run on my MacBook Air, for example. And now if I'm running on a weaker machine, it's not a problem because the memory requirements don't. On that slide we showed earlier, as we doubled the cycle count, we also doubled the memory requirements. And now the memory requirements are capped. So I next want to talk about sort of a little bit about how this works. First in the context of proving, and then in the context of verifying. So what do we actually do for continuations? We still generate the full execution trace like before. But now instead of running through the process that I outlined before, we're going to split this full execution trace, which we refer to as a session, into some segments. And we're going to note the beginning and ending state of the ZKVM for each of those segments. And we're going to just prove each segment independently. And then the receipt for the session consists of this vector of segment receipts. And if we want to, we can roll up those segment receipts into a single receipt. So we actually have two versions of continuations. If we just end up with, you have this giant program, you chunk it into segments. If you end up with a proof for each, we call it flat continuations. And if you roll them up into a single proof, we call it roll-up continuations. And for verifying, there's sort of a slightly different process depending on whether you're talking about the flat continuations or the roll-up continuations. In the first scenario, you have to check each segment proof. You have to check that the starting and ending states line up appropriately. And you have to check that your initial segment ID matches the ID for the binary file that you were trying to make a proof for. On the other hand, if you have rolled up the continuation into a single receipt, then you just need to check that single receipt. So we're going to dive into some things that continuations has unlocked in a minute, but any questions before we do about what continuations are, why you should care, or how they work?
So what's the trade-off? It sounds like memory for CPU trade-off. Is that it?
I mean, in some sense, there's a trade-off, I guess, of code complexity on our end. enabling continuations has been a pretty substantial engineering endeavor. From the user perspective, I guess there's some trade-off in the sense of if you want to have a single proof and not have to worry about a roll-up, then maybe you would rather just have the like large clock time from running it without continuations. But
I could provide a little bit of
sure.
context there. Yeah, so there's a little bit of extra overhead. So whenever we have to, basically we're constructing a Merkle tree of the image of the memory. And this gives us the ability to verify that the state of the memory is consistent between one segment to the next. And so if you weren't using continuations, the maximum number of cycles that we can run is 16 million. So you can only run 16 million. And when you're running 16 million cycles, it takes about 100 gigabytes of RAM. Okay. So, but if you do continuations, well, you have to, it takes about, I don't know, roughly, there's about 1,000 cycles per page. Each page is 1,024 bytes. And so basically depending on how much memory is being accessed in a given segment, there's a certain amount of overhead that's necessary to basically do a bunch of SHA hashing of the memory pages in order to make sure that the memory is in a certain state. But compared to, so currently our default setting for the split size, like the size of a segment, is 1 million cycles. And so if you split it at 1 million cycles, the overhead is like, less than 1%. It's like 10,000 cycles or something for all of the overhead to do all of the memory checking. So hopefully that makes sense. Yeah.
And so for the ZK proof creation, is that linear still? Is the main cost stemming from the overhead of managing the memory?
Yeah, the proof system doesn't change at all. It was really just a change to the circuit. It means that like the circuit that makes RISC-V work basically has extra rules now to make sure that when memory is read or written, it compares against a known. That's what the image ID is. It compares against a known hash of the Merkle tree. So basically, yeah, the overhead is pretty minimal, and it doesn't change the proof system at all in terms of we still do read-Solomon encoding, and we still all that stuff still it's still exactly the same proof system. Yeah. So there's really not much disadvantage. Yeah, it's very minimal overhead as far as I can tell. Yeah. So
auditing.
Yeah.
Thank you so much.
Yep.
Thanks, Frank.
I have a question there on the roll-up, what we're referring to as a roll-up. Is that just you're implementing a circuit that implements the verifier of each of the segments, like each of the flat continuations? Like it's just like the flat continuation validator in a circuit? Is that how you do the rollups?
Yes, we have a separate circuit. So originally we actually had the ability to run the verify inside of a RISC-V program, but that ended up being like we wanted to have our verification times. We wanted rollups to be very fast. We wanted it to be like sub-second. We didn't get quite to sub-second. We went from 30 seconds down to something like 2.5 seconds. And the way that we did that was we built a separate recursion circuit that's able to basically we have these things called predicates, and the predicates are kind of like the way that you program the recursion circuit. So the recursion circuit has its own instruction set, but it's a very minimal instruction set. And so for instance, it doesn't even have loops. It doesn't have any control flow or anything. But so what we do is we have some static like predicate code that gets compiled into a circuit, and then that is what we use for the rollups.
Got it. And you said it's recursive, so it can like support as many it can combine as many flat continuation validations as you want, or is there some
Correct.
upper limit?
Correct. Yes, we can. There's basically no bound to the number of. Yeah, it's log n. So yeah, it's no bound to the number of like leaf nodes in your tree. Yeah.
Okay. And then one other, like, maybe this is too in the weeds and we could save it for after, but like, is the witness generation that you do for these continuation cases exactly the same as before you did continuations? Because I just am imagining that like aligning, and maybe this is what you mentioned with the overhead, like aligning the memory, read-write consistency, lookup tables, or however you're doing read-write consistency with the section that actually reads and writes from that relevant memory, I would imagine needs to be contained in the same segments. And so like, seems to me like splitting the whole execution trace into different segments would require some like really careful, I don't know, additional sort of logic. Is that what you sort of meant by the overhead, or is
So, okay, so let's talk about the journal. What does witness generation look like? Basically, when you commit to something, we basically have this journal where users, okay, so users can read stuff from an oracle. Let's say there's some sort of host side memory, something that I want to read from the host. It's not deterministic, and I want to get some values into the ZKVM, and then I want to do some computations, and then commit some results back out to the journal. All that stuff is actually scoped at the session boundary. It's not per segment. So the idea is that you have this, like, let's say you have these buffers for the input and the output, and they get read and written to via some sort of API. We have an e-call. And so it doesn't actually have much to do with the memory. And like the memory works the same inside the guest, whether you're dealing with an oracle or not. So basically we have a special e-call that says, okay, hey host, give me some memory, like move some memory into the guest. And we then do some computations, and then the journal gets collected. And the idea is that the journal is, like I said, is the session boundary. And so all of the verification that goes into checking that the journal is correct happens at the session boundary. So we have a special sort of verify for the session that checks to make sure that the hash of the commitment, like basically the output hash of the session matches the hash of the journal that I was collecting over all of these segments. So yeah, it's not really tied to the segment, and it ended up being not difficult to make that work. It turned out by doing it that way.
So there's some like session information that's common to all segments, and that's how it's sharing memory or something?
Yeah, so the session contains a vector of segments, number one, but it also contains the journal. So the journal, when the guest does a write to the host, the host, the ZKVM host, just continues to collect all of the writes that have that happened in every segment. It just concatenates, every write just gets added to the journal buffer. And then at the very end, we take that whole concatenated buffer, and that's what we call the journal. And that journal it gets attached to the session. And so now when I go to make a session receipt, when I prove the session, what that means is I have to go prove all the segments, but then I also hold on to that journal. And now when I want to do a verify, I have to check that the journal that was collected over all the segments matches the hash of the output, which is the main thing that you get for, the very last segment of the session has a valid like output hash. All the previous segments don't need to have, they just have a null sort of output hash. We don't worry. It's the very last segment that's kind of special, I guess. So
can I ask you a question? So then if you have like a very memory intensive program that's reading and writing to the host a lot, that's gonna continuations won't work well on that.
It should be fine.
A lot of the work will happen at that end step.
So continuation, the overhead that you'll see, it isn't really related to whether you're doing lots of reads and writes with the host. It's more like if you're doing lots of reads and writes, period. So like if you're reading a lot of memory, if let's say, as a silly example, my guest code just has a loop that walks from the very beginning, the top of memory, and goes all the way down to the bottom. It just walks all the way through 192 megabytes of memory. If it does that, then yes, a bigger portion of the overhead is going to be in doing the memory verification for continuations versus, actually doing the work of reading and writing into that memory. So, but that's, pretty like, yeah, if your program is doing nothing but reads and writes, then the overhead is going to be more for sure. But it doesn't really have to do with the host interaction. The host interaction, a lot of times when you read stuff from the host, you might put the results into the stack or into local variables or registers. And so sometimes it's not really a huge overhead in that regard. So.
I also had a really dumb, unrelated question, which is you mentioned like number of cycles for converting programs. What are those cycles of, like an R1CS program or something?
Well, in our world, cycles, each cycle is sort of how long it takes to do a particular instruction, a RISC-V instruction. Most RISC-V instructions take one cycle, but some instructions like multiply or divide, they actually take 2 cycles in our system.
Is a CPU cycle or a virtual CPU?
It's just like a CPU cycle, correct? So, but in the case of like SHA hashing, we have a special circuit for SHA hashing, and that takes 72 cycles per SHA hash. So like certain instructions may take many more cycles than others, but yeah. Sorry for the derail.
Oh, that's great. I'm glad you were here to handle those questions because you're better equipped to answer them than I am.
Yeah, thank you.
I want to just do a quick time check on, do we have like a hard stop at 10 or sorry, whatever, hard stop at the hour, or can I go over a little bit? What are people's thoughts on that?
You can go over. Yeah, that's okay.
So I think, oh, great. So we talked a little bit about what continuations are. Let's just briefly touch on some of the things that this enables. This ZK FHE thing, ZK fully homomorphic encryption, someone made use of continuations before we made any sort of public announcement, as soon as there was just like a PR that made it actually available. And this is an example that it just takes 2 numbers, encrypts them, and then does an addition of those encrypted values. So this is like a minimum, a proof of concept, I guess, for FHE inside the ZKVM. But as far as I know, this is the first example of any fully homomorphic encryption project inside any ZK project. So I think that's pretty exciting. We also have expanded our ZK EVM EVM inside the ZKVM because of this. The initial example we had up was, as Andrew described, this like ERC20 transfer. But at this point, there's really not much limitation in terms of what you can do in terms of running the EVM inside the ZKVM. One thing that has been done in terms of running EVM inside ZKVM is this zero knowledge proof of exploit project, which if you're not familiar with is worth checking out. This project it won the DeFi track at ETH Denver, and it's a project that lets you prove that you would be able to extract funds from an Ethereum account without actually extracting funds from that Ethereum account. So it's a method of white hat hackers being able to kind of zero knowledgely prove the existence of an exploit without actually having to reveal the exploit or to use the exploit. So. And we also have this WASM example inside the ZKVM. And actually, I think this morning or maybe late last night is the first time that someone has done the other direction. I think we just got our first example of somebody running the ZKVM inside WASM. So that's not related to continuations, just sort of tangentially related to the WASM example. So given the time frame, I don't think I'm going to get too into either of these topics. We did just add an accelerator circuit for big integer arithmetic and are working on adding functionality for elliptic curves. I think everybody's wanting elliptic curve operations. And then, like I referenced earlier, we are also working on a new language for our circuit generation process, which we'll definitely be using internally as we roll out new versions of the circuit. But the intention is also that this becomes a tool that external developers can use in order to add some custom functionality to our circuit. So what I want to kind of close with is some discussion of our upcoming product called Bonsai, which the intent here is to bring the ZKVM into on-chain contexts. So the way this works is you have some on-chain app, and the on-chain app is going to send a message to our Bonsai proxy contract. And then we have a service that continually watches that Bonsai proxy contract. And when a request is made on chain, we generate a proof off chain. And then we post the results of that proof back to the chain. So the intention here is to make this as simple as possible for like Solidity developers or other like blockchain developers to be using here. You write some really simple on-chain logic that effectively just triggers a request to our proving service. You upload your binary file to our proving service, and we basically handle the rest there. So when you trigger a request, we'll generate a proof and we'll post the results back to chain. So questions about that? I think Andrew's still on the call.
What are you proving?
Whatever you want. So you'll write some, basically, like if you have you'll write a binary in Rust, or you'll write a file in Rust that will compile to a RISC-V binary. And then your on-chain request will request a proof that's associated with that binary. So when you send a message to Bonsai, you'll indicate, I want to generate a proof using this binary file, and you'll include the sort of identifier for the binary file that you want a proof generated about. So this is useful in the context of, like, if you have some on-chain application that involves some complicated logic, you, instead of needing to run that as on-chain logic, you can write the complicated part of that logic in Rust and then have that execute off-chain. So it serves as a sort of like off-chain execution layer for whatever complicated logic you would otherwise be running on-chain.
And the binaries like live in some RISC Zero hosted like database or something.
Yeah, Andrew, do you want to say anything more about that? My answer to that is yes, I think.
That pretty much covers it. Yeah, just hanging on to them.
Cool. All right.
So why would you want to use Bonsai? I just referenced the idea of it enables off-chain compute. If you have some complicated on-chain logic, Bonsai allows you to export that into a sort of off-chain compute layer of some sort. It also lets you like manage the receipts for programs with continuations. This roll-up continuations that I referenced earlier is happening through Bonsai. So if you are using continuations and would like to make use of this roll-up continuations, for now, the way that that's going to happen is through Bonsai. And finally, the reality of being able to amortize costs by packaging your proofs with others, I think is really substantial. The reality of like posting proofs on chain is not cheap. And the fact that we can roll up a lot of proofs into a single on-chain post is a substantial cost saver. So that's the short pitch for Bonsai. Questions about the architecture or motivation there? All clear. Okay. Well, that's what I had planned for everybody. There's a few more links on this last slide. First link here is to our docs page. The second link here is to our examples repo. And the third page here is to the waitlist for Bonsai. So I'm happy to stay online for a few more minutes for some more questions, but that's all I had prepared in terms of presentation.
Thank you.
Great,
Yeah.
thanks. Thanks, Paul. Any questions on Zoom? We had a lot of questions sprinkled in, so
Yeah.
Yeah.
Cool.
All right.
Awesome.
Thanks a lot, Paul. Thanks a lot, everyone.
Thanks, yeah.
All right.
Thanks, Paul.
Yeah, thank you. Appreciate
Thanks,
it.
Andrew and Frank, too.
Yeah.
And thanks for listening, Andy and team. Bye bye.
Yeah.
All right. Bye, everyone.